So one of the things I wanted to go over is the difference between solid and stranded wire. Because when we start talking about installations, particularly for like mini splits and multi-split, so multi-indoor head units, and VRV, and now we're talking about things like the Daikin Life systems and our Daikin Fit systems that are all communicating systems, that are all using low voltage, 5 volts DC, to communicate from the indoor to the outdoor units. We're doing something that is a lot different than what we have done in the past. Because in the past, we've used our thermostat wires as a path for current. We were actually using 24 volts AC, and we were applying a load across those thermostat wires. So we were using those as regular conductors, right? So we were passing current through the conductor so that we can operate a load on the other side. So we had voltage and we had load, so we had potential running through those wires. And we were doing a fair amount of work with those. As we start moving away from traditional legacy, and you're going to hear that term a lot in the industry, legacy. So what legacy wiring would mean is that we're using a standard transformer with 24 volts AC. So legacy wire is going to be our common RYGW, where we're sending 24 volts across conductors to energize some type of a load, some type of a relay or a contactor or some type of a device. So we're doing work with our wires. And traditionally, we've always used solid wire to do that work with. Well, as we start shifting away from doing work with our conductors to doing communication with our conductors, they're taking on a little bit different role. And so paying attention to the type of conductors we are using is pretty critical. So you'll find in a lot of installation manuals, they actually specify for you to use a stranded wire over a solid wire. And so I want to talk about that today so we can get a better understanding of what the difference is between the two, because they're just copper wires, right? Well, yeah, they're copper wires, but they do have some differences. So let's dive into what makes those differences. So Omni Cable is a really good wire and cable supplier, and they have a lot of good documentation, a lot of good training on different types of wires and the technology that goes behind making those wires. So in some of their training, what they talk about is with solid conductors, they are a solid single piece of metal. In most of our industry, we're using copper. Occasionally we'll use aluminum, but most of the time we're using copper. And it is tougher than a stranded conductor, but rigid and less flexible than our stranded is. So our stranded is more flexible. So that's one difference between it. Solid conductors are more likely to break if they're subjected to frequent flexing than stranded. But stranded conductors are made of multiple small strands, which group them together to make up a single conductor, which makes it more flexible but less durable. So a physical trait that they have the difference is their ability to be flexible or rigid and the strength that comes from that. So when we start talking about the use of a conductor, we have to think about how it is constructed internally. If we need it to be flexible, we're probably going to need to have a stranded wire. If we need it to be more rigid and more structured, we're going to need a solid conductor. So they have physical characteristics that make them different. And then when we are using stranded wire, there's actually different ways that we construct the stranded wire for the application that we're using it with, because sometimes we need to be more flexible. Sometimes we need it to be able to carry a larger load. Sometimes we need to be able to have a strong tension to it so that if it is under a lot of pull, under a lot of stress, it has the ability to still maintain its integrity without physically stretching the conductor. So we have a few different ways that we put those individual strands together. The most common one, which is one we're going to encounter a lot here in the HVAC industry, is called bunch stranding. So bunch stranding is when we just take a collection of individual strands, we twist them together, and it's typically in the same direction. So if when you're twisting wires together, you've probably noticed that some wires, when you twist them clockwise, so typically if you're right-handed, you're twisting a wire clockwise, and if you're left-handed, you're twisting a wire counterclockwise. It's just a natural motion of our hands. But you'll find that there are wires that twist well one direction, but don't twist well the other direction. And that's because of the direction that they are actually constructed as they're being wound. So that direction will play a factor into what is the correct way to twist those wire nuts. Because if the wire is twisted in a clockwise rotation, we should be twisting those when we're joining multiple wires together in that clockwise rotation so that we can continue to bring those into a common direction. If we have one that is twisted clockwise and one that is twisted counterclockwise, and we try to twist those together before we put our wire nut on it, we're going to find that they don't bind very well. They tend to get hung up and they tend to knot up a little bit. So understanding that there is different geometry, even in standard bunch stranding, is important to know. There's also concentric stranding. So concentric stranding consists of a central wire, and around that wire then we have different helical layers that are brought around it, and that can also have some different directionality to it. And if we're trying to create a conductor that has more strength to it, we may use a different material on the inside of that. So if it is a conductor that we know is going to be on a long unsupported stretch, we're not going to use copper, because copper is a soft drawn metal. It's fairly easy to draw it out. So we don't want to put that extra tension along its axis, otherwise we're going to stretch the wire, and we may stretch it at a different rate than what the insulation is. So on a lot of these concentric stranded style wires, we'll actually use like a steel core to it so that it has some rigidity to it. And then we'll wrap our copper around it. And it's typically in one direction. We also have what's called Unilay Stranding, and it's basically the same as concentric, except that they lay those strands in the same in each layer. Because if you look at that standard, if you look at that standard concentric, we start rotating the direction of them. So I may have a solid inner core, and then my first layer I'm going to wrap clockwise, and then the next layer I'm going to wrap counterclockwise, and we can have multiple layers going back and forth. It creates that strength of that wire. It gives it the ability to go over long spans without being stretched. You'll see a lot of that on overhead style cables. With that unilay, we're going to run it all in the same direction, and it's typically wound to the left-hand rotation. And so that one's called the unilay. And then, of course, we also have our rope lay stranding, which is concentrically stranded, each of which component has the strands are themselves stranded. So we're going to take a rope or a stranded wire, and then we're going to intermingle it with a whole bunch of other stranded wires, and you'll find this quite often as well. See this a lot in cord style, like USO style, or in J cords, that they'll have the multi-strand like that. And a lot of automotive wiring, if any of you ever wire up any kind of high current wires for automobiles, especially automotive amplifiers, a lot of those use that braided style so that it has a variety, or rope style, so that it has multiple layers of braiding to it. It's pretty strong wire, but very flexible. So the most significant difference between stranded and solid is actually it's in its performance. So because of the higher gauge conductors, they have more insertion loss than the lower gauge ones. So the stranded exhibits 20 to 50% more attenuation than those solid conductors. So because that cross section of that stranded conductor may not always be copper, right? Because if you think with the solid conductor, it's solid all the way through. But with the stranded of the same size, I may not be able to move exactly as much current through that thing because there's gaps in between my individual wires. I may have air in between those. So a lot of times the equivalent wire between solid and stranded doesn't actually pass the exact same amount of current. We can typically flow more current through the solid conductor than we can with the stranded, just because the stranded doesn't have the same amount of surface through it. It actually has gaps in between those strands. Even though it's compacted very tightly, there's still gaps in between those strands, so it doesn't actually draw as much. So a lot of times we'll use a solid conductor with AC and we'll use a stranded with DC because of the way the currents actually flow through the conductors. Because a lot of times with a AC current, we're traveling along the surface or the skin tension of the actual conductor versus stranded, where we're actually trying to, with DC on stranded, we're actually spending more time through the inside of the conductor itself. So we have more paths for that to flow. So besides having physical characteristics that are different, we have different ways of flowing through that conductor. So they're considered more rugged and less likely affected by vibration, susceptible to corrosion, since they have less surface area than the stranded conductors. So we typically have used solid conductors for AC current up until now, when we're starting to talk about communicating systems, and we're getting into a variety of new technology going into stranded wires. So stranded wires is starting to take over the industry because we can design those stranded wires for specific purposes. While I was building this class, I found it really interesting of how they construct, they call them submarine cables, but underwater power cables. You know, I've seen them before, never really paid enough attention to them to know what is the design of that. Because if you think about it, those cables are not only designed to pass current through them, they're designed to pass current in some very rough conditions. Long stretches, underwater, has the potential to be moved and dragged. So they have to be flexible, but still have the ability to move a lot of current. And so by the design of those, we're using stranded wires that are supported many a times with solid, even steel wires in the center. And then we're using a lot of insulation. And so then we're also using paths so that we can move other fluids through. If we need to move gases to help cool that line over long distances, we can do that. If we needed to run any type of liquids through that for cooling, we could do that as well. So we have multiple types of tubing and multiple types of wiring that can go through one electrical conductor. I think it's very interesting when you look at the design of those, of what we can now do with stranded wires. We've come a long way from a solid conductor to a stranded conductor, to different designs of stranded conductors, to cables that have multiple styles of conductors. Because when you look at that, we're using the stranded wires to be able to pass our current through, but we're also using solid conductors because of their strength and rigidity along the outside of it to create multiple bands to make that a very solid structure. So I thought that was kind of cool just to look at to see, you know, what we can do with stranded wires. If we look at installation manuals, we're going to see some really interesting perspectives on what type of wires can be used and what ones are not recommended. So if we look at our communication wires, we're going to see a lot of times we have designations for stranded or solid wire. So we can use either one of them. So in this particular installation manual, this is for a mini split installation, it does have a recommendation of using stranded wire, either for communication or for the actual high voltage. But at the same time, we're still needing to land that with a solid connection. So even when we're using stranded wire, we still need to be able to land with solid contacts. So if we're using stranded wire for communication or for power, we're going to need to make sure that we've got the proper terminals to attach to those stranded wires when we land them so that we can make positive contacts. Because if we're using a solid conductor, what they're recommending is that we take that solid conductor and we apply it over a larger surface so that we get good constant contact so that we can make sure all of our current can flow through that solid conductor and land on our terminals properly. So we actually are supposed to put an eyelet on our solid conductor so that when that washer or that washer plate on that terminal plate draws down, it puts even pressure over the entire surface so that we make good contact. Because if we're using this for communication, we cannot take a chance of losing communication because of poor contact. So we distribute that copper, that surface out on a larger area. We cannot just insert it into the terminal and draw it down with the terminal screw. So we have to make sure that we have a good solid contact. And the only way to do that with a stranded wire is to put an eyelet on that. So when we attach an eyelet, when we crimp a eyelet onto a stranded wire, it gives us a large, flat, solid surface to make a similar contact that we would have made with the solid wire. So even knowing how to land wires properly are going to be very important as we go forward with new types of communication in particular. So if we look at another slide out of these installation manuals, you're going to see that this particular unit can be used with solid and stranded, but in some applications it requires stranded even for communication. So we have to make sure we know what wire is being called out. So in these manuals for our pieces of equipment, we have to pay attention to what is allowed and what is not. So this particular one will tell us that the wiring between the units, so this is between the indoor and the outdoor, it's not very specific. All it says is the wire size and the wire length must comply with local codes. That's it. And then the remote control wiring, so remote control to the indoor unit, is a sheathed 2-wire, 16 to 18 gauge. Doesn't even specify if it needs to be stranded or if it needs to be solid. So in this particular situation, it is allowing either one to be used, solid or stranded. We just have to make sure that we know that we're landing properly in that application. But some will only allow a stranded wire, and some are particular whether it's using a shielded or a non-shielded cable. So I've seen even in our own equipment call outs for different cables. If we look at this particular one, we're going to see that in this cable, it's actually fairly clear that if it has if you look up there, it says it recommends using a 14 gauge stranded and insulated wire for connections between the indoor and the outdoor units. And then of course using local codes. But if you take a look at this, it says take care to ensure that all wiring between the indoor unit and the outdoor unit has a consistent connection. Any splices can cause communication errors. So we need to make sure that we're understanding what they're talking about by communication errors. And if you actually look at this, when we look at the sheathing on this one, we've got a ground that is going between our outdoor unit and our power supply, but we also have a ground between our outdoor unit and our indoor unit, dedicated ground wire. So we have to make sure that we're using cables that have all the proper wiring. So this particular one, it would have been a 14-4 that has its own separate ground. And we have to make sure that we're connecting those to the proper terminals, indoor and outdoor, because we're going to have on a lot of these mini split and multi-split installations, we're going to have 2 hotlines. Typically number 1 and number 2 are going to be our high voltage hotlines. And then number 3 is actually going to be a communicating line, an independent communicating line between the indoor unit and the outdoor unit. If we get those crossed anywhere, we're going to fail on our communication. And we also have to pay attention to our wires when we talk about the difference between a communicating and non-communicating style situation, because copper does oxidize. We've all seen that out in the field. Copper doesn't really rust. It produces a patina called copper oxide. And unlike rust, it actually helps protect that metal from further corrosion. And it does not interfere with the conductivity of the copper. That's important to know. So when we're talking about using AC current to pass through a copper conductor, if it has a light patina to it, if it has a light copper oxide, it doesn't affect the way that the current flows through that wire. It will start affecting it if that patina starts turning into a thicker corrosion. And what's really important to understand is when we are using these wires for communication and not for current, that patina does start affecting things. That patina does start affecting the way that we're communicating. So if we think about that, if we are using a wire for a load, we're sending electrons through it. We're flowing through that conductor just like water would flow through a pipe. But when we start using that exact same wire for communication instead of a current, a load, our electrons are going to try to find the path of least resistance, which is where? On the surface. So if our surface has oxidation and corrosion on it, we can now interfere with the way that we communicate through that wire, the way that our electrons travel over the surface of it. So in the past, if we would have a thermostat wire, say we had a solid conductor thermostat wire that did get a break in the insulation, did have a mouse chew into the insulation, did have insulation that got caught into a staple, did sit inside of a wire nut outside that was getting rained on. It didn't affect it much because the oxidation created a nice thin layer of protection over the copper, and it didn't interfere with the way the current was flowing through that. But if we reuse that exact same wire that has oxidation and corrosion on it, and we turn that into a communication wire instead of a current wire, now all of a sudden we have some problems with that patina and with that corrosion. So we're finding that installations where we have taken out legacy style 24-volt AC operated units and we've put in communicating systems and reused the existing control wire, that control wire may have worked fine on legacy with some of that extra patina and corrosion, but does not function properly for communication. So it brings in a new layer of understanding of wires and how we communicate through those wires. Because if I have a single solid conductor and I have oxidation on the outside of it and it works fine for legacy wiring, pushing current through it, and then I use that same solid wire for communication on my new outdoor unit and indoor unit that I just installed, I won't be able to talk along that solid surface as well because of my additional patina and corrosion. That's why we like using stranded wires on communicating systems. Those stranded wires just gives us more paths to be able to communicate on. So a lot of times we have to, when we install new communicating systems, we need to pull new control wire as well. Sometimes that old solid conductor works fine, but typically it only works fine if there's no breaks in it at anywhere along the path. Because what we do with 5 volts DC is we take an AC voltage, we're taking that 24 volts AC that we started with, and then we're going to add in some diodes so that we can chop off part of the peaks of the sine wave so that we're reducing the voltage. And in the process of doing that, we're creating plateaus that we can send signals on, flat spots that we can talk on in that now DC signal. It was an AC sine wave that we chop off with diodes, and then we now give it a flat spot, and then we change the resistance a little bit so we can control the voltage. And so we end up with a 5 volt DC signal, but it's actually traveling both ways in reference to ground. So our communication systems are using ground as a reference point for our 5 volt DC wires. So now it becomes important to make sure that our ground wire is even clean and free of debris. Because if you think about that in legacy mode, a ground wire was typically just that, an emergency escape for current to get to ground. It wasn't used for daily communication. Our high voltage wires going to the outdoor unit, that's all we used was the high voltage wires. Our ground wire was an emergency path. Well, now in communicating, that ground wire is actually essential for communication. So if I have a ground wire that is heavily oxidized and corroded, I'm now interfering with my communicating capabilities of my entire system. So super important to understand grounds. We'll do a separate class just on understanding grounds and testing and verifying grounds. But we need to know that the difference between the copper in a solid strand and in a true stranded wire is that our current flows differently through them and we communicate differently through them. So a solid conductor works well as long as we can pass our signal on its surface, as long as there's no corrosion there. A stranded wire works better because we have more paths for that current to flow on. So how do we maintain the integrity of our wires, especially when we're splicing? There's a couple things we need to pay special attention to when we are splicing wires that are going to be used for communicating devices. If you're reusing that solid conductor wire and there are wire nuts anywhere along that, you immediately have to cut those off because they've already been exposed to oxygen and moisture. I'll guarantee they're already patinaed and oxidized inside of that wire nut. And we're also putting those copper conductors inside of a spiral that is a dissimilar metal. So I will guarantee it has additional corrosion inside of that connection where we're twisting it together. So whether you're using a solid conductor or a stranded conductor, if it is a communicating system, you must cut off any existing wire nuts. You need to use either a waterproof or an underground style wire nut that has dielectric grease inside of it, or you can use a standard wire nut. We just need to make sure that we have clean copper that we're starting with. So whether it's solid or stranded, we're going to cut off existing wire nuts. We're going to re-strip those until we get good clean copper. We're going to pre-twist them together. We're going to put those inside of a wire nut until we get them nice and locked in, and then we need to fill those in. We need to keep oxygen and moisture away from our copper. So what we need to do is we need to make sure we just have some clear silicone or dielectric grease. Clear silicone works great. That's all we're going to be using in most of those underground wire nuts is a good 100% silicone. So after you've twisted your wire nut together, have you a tube of silicone around or a caulk gun of silicone. Most of the time we already have silicone on our vans anyhow. And we need to fill that wire nut full. We need to fill that wire nut so that we can remove any potential oxygen or moisture from entering into our copper and create an oxidation and corrosion on that copper surface. And that's something we've never talked about before when we're working with legacy wiring in general. If I needed to extend an 18/8 thermostat wire, I just simply got me another piece of 18/8 and I twisted them together and I put me some wire nuts on them and off I went, and I never had any problems. If I use that exact same piece of wire on a new communicating system, I'm probably going to have problems. So in our technical support side of Johnstone, what we have been finding with our communicating systems, new installations of communicating systems, our number one culprit is wiring, communicating wiring. And so the systems that have reused the existing line sets and reused existing control wire, because you can, a lot of the manuals will allow you to use solid conductor communicating wire, and they can allow you to use existing tubing line sets. They're required to be flushed out, and the control wire is required to be in good standard. Well, what that means is no splices. Or if they're spliced, they need to be properly spliced. So we find a lot of times our issues in our communicating systems are oxidation on the copper or corrosion on ground terminals. So pay special attention to our wires. Understand that in many applications you can use solid wire, but you need to read the installation manual because some will specify solid or stranded, and some will specify that it is a shielded wire or not. And we'll talk about that a little bit more as we get into some other conductors. Just remember that no matter what we're using, if we are using it for legacy, we're passing current through that wire. If we're using it for communicating, we're passing communicating signals in low voltage, low current. So the condition of the surface of our conductor plays an entirely different role when we're talking about communicating. So any questions on solid versus stranded wires? I'll open up the lines in case anyone has any, because there's a lot of questions on the differences between those. Nobody at all? No, hopefully I explained it really well then. All right, well, everyone have a great day. Hopefully you don't have too much snow to shovel out there. I got a little bit I'm gonna need to go out and clean up this morning. And well, I look forward to having some more flex training opportunities with you all, and we'll see you next week. Have a good day.